Hello, my name is Jack Thiesen, and today I'll be presenting undergraduate research from the University of Michigan's Radiation Health Engineering Laboratory. Our lab works extensively in the field of dosimetry, and this project is specifically in the field of thermoluminescent dosimetry. A thermoluminescent dosimeter is a passive integrating dosimeter that emits photons upon heating proportional to the experienced ionizing radiation, either experienced since annealment or throughout its lifetime. Um, it turns out that inside this material, individual trap states fill with electron hole pairs as ionizing radiation is experienced. And the locations and densities of these trap states, effectively like the depth from the surface and the densities relative to each other, causes a large source of error upon readout. And it turns out that this sort of error can be estimated and mitigated through a process called glow curve analysis. Glow curve analysis is the idea that you can fit a physical distribution called first order kinetics to a measured glow curve. Basically, a glow curve is the readout from a thermoluminescent dosimeter, so a thermoluminescent dosimeter spectra, you would say. And by fitting these individual physical distributions to the glow curve, you're able to determine features of the specific signal that you would not otherwise be able to see. This is useful because individual trap states, which correspond to the individual physical distributions, have heights relative to each other based on a list of physical parameters. And the chief among these is fading. So as a thermoluminescent dosimeter sits either in light or elsewhere, with some probability, ionizing radiation or electron hole pairs inside the material in trap states, excited trap states, will release photons just under ambient conditions. And this turns out to occur with much more frequency in lower energy trap states. So by seeing the ratio of a lower energy trap state to a higher energy trap state, you're able to obtain some information about how much fading has occurred. This process of glow curve analysis is always done by a computer. However, all programs written up until this point, except for ours, involve extensive human interaction. A human sits down and sets the parameters for what the initial guesses of the glow curve software should be. That is to say, the human pinpoints energies and temperatures along the x-axis and intensities of counts along the y-axis to determine what individual glow peaks should look like. Our software automates this process fully and identifies where these parameters should be set based upon which glow curve material the input glow curve is most similar to. Our software has 3 steps. The first step is a denoising process, where we effectively smooth the raw counts data. The second process is a glow curve identification process, which I was just talking about, which is our software has a list of parameters of common materials, and it compares these common material waveforms to the input waveform and says which one matches the best. This involves a short fitting process using gradient descent. The final step involves an extensive fitting process where the individual peaks are fit very well to the original input glow curve. And it uses the Levenberg-Marquardt algorithm. We hope that our research will allow researchers in dosimetry and health physicists measuring personal dosimeters will be able to effectively observe more data because they can automate their readout process. More than 7 undergraduates have worked on this project, 3 of which have gone on to become MTV doctoral students. This work has produced 2 journal publications. One was accepted on February 9th of this year, and we're really excited about that, and 18 posters as well, including this one. Researchers at Los Alamos recently reached out to us asking us for our software, and they provided us with experimental data that we are going to be able to use to test our software better. Thank you for your time.